Hello, Ivan. So in this video, let us talk about a very standard and very important problem. The problem name is find peak element. So let us talk about the problem statement first and then understand how we can solve it out. Problem statement goes like this, that you are given a peak element is an element that is strictly greater than its neighbors. Okay. Now you are given a zero index integer array nums. Find a peak element and return its index. If the array contains multiple peaks, return the index of any of the peaks. And you just have to find out that. You can also imagine that the two extremes of the arrays are minus negative, which means that they are like very deep points. So just assume that they are very like infinitely negative points. And like you can consider always any element always considered to be strictly greater than its neighbors outside the array. You must have to utilize an algorithm to run it in log n time. Whenever you see log n time, I generally try to think it in some sort of a binary search because binary search can only do that in log n time given to find out some elements inside some array. Like I possibly try to think in that direction, but let's seek some examples. Let's take this as an example. And the oral thing we'll also understand it by drawing it out as well. So let's say that we have some peaks and troughs. So you can see that, okay, so if I draw it like 1, 2, 3, 4, 5, and 6. Okay, so the first point is 1, the next point is 2, the next point is 1, the next point is 3, next point is 5, then 6, and then 4. So this is how the actual things look like. Okay, so as you can see that there are two peaks. This is one of the peaks. So peak is that any element whose left and right are smaller than. So as you can see for this element, the left and the right are both smaller. So this is one of the possible peaks. One of the possible peaks can be here as well. Now, how can it use binary search and like try to find it out? So what do actually binary search do? Binary search comes closer to the final approach. Like binary search can only work, you can say, when you actually have some sort of this pattern only. Okay. By pattern, I means that it tries to converge to a particular point. Okay. You can say a local minima or local maxima, a point. Okay. That is what binary search is very capable of finding out. A possible best scenario among all the scenarios. So it has all the scenarios, like this can be a point, this can be a point, but whatever is a point that we're looking for, that can be used to find out by binary search. Now, how can I use that? So what binary search is capable of? So let's say we have two extremities. I'm just giving you a very small example of what binary search is capable of, and then we try to exploit it to this example. So we'll come to the middle in binary search with the two L and R. We have L and R, the extremities. We come to the very middle. Check out whether the element I'm looking for is in the middle. If not, then we'll check out whether we should go to the left side or right side. And we try to converge to a particular point. That's it. Okay. Now try to exploit this particular thing to here as well. We either can be on the left side of the hill or the right side of the hill. Pretty much simple. If we somehow are doing binary search over this array, let's say this array defines this, we somehow land, let's say land on this point, that is 3. Let's say this point. If I land on any point, the original idea is that either we can be on the right side of the hill or the left side of the hill. How we can check that? We can check it by comparing it with the two neighbors. If the element that I am on, if the right element of it, the next element of it is larger, and the previous element of it is smaller, which means that I am on the left side. Similarly, if I land upon, let's say, this point, and if the element on the, you can say, right of it is smaller and the left of it is larger, then which means that we're on the right hand side. And based upon that, if we are on the top point, how we can know that? Both of its neighbors are smaller. So if we're on the top point, both of the neighbors are smaller. If this condition is met, we have to go somehow on the right hand side, because the right hand side, if we land upon this point, our peak will be on the right hand side. But if we somehow land upon this side of the mountain, or we have to go on the left hand side. And we have to keep on doing this iteration until we hit the point of the peak. That's it. That's the complete logic for this particular problem. I'll show you with the code part now, but if you still have any doubts, you can rewind this particular video or put that in the comment box. I will try to solve and try to give as many supplies as I can. So that's the complete logic that you have to use. So let's remove some part out, and then we'll see how we can understand it here as well. Let's not remove the complete drawing and see. So what you can see here is that we are doing a binary search. In binary search, we defined out the limits. So we have defined out the limits, L and R, the two extremities. Then we'll completely do a while loop until we find out the peak. So we'll do a while loop because we do not know how many iterations we'll do. So we'll do a while loop. And the iteration while loop condition is L should be less than R because L and R are the two extremities of the area we are finding out. And we keep on you can say decreasing the limit until unless keep on decreasing the limit until we find out our complete peak. Okay, so if this overlaps, like if they cross out each other, we should stop. So L and R find out actually our range. Okay, we find out the middle element. We can easily find out the middle element. Now our condition is that if we land upon the element that we're looking for, okay, that is the element that should be a peak element. So the peak element has this condition. Now let us understand this condition. We understand that the peak element is such that the left of it is smaller, the right of it is smaller. The left of it is smaller if it exists. That is one thing. What we are given is that the -1 index and the very last index, the n index, are already infinity, which means that they are already very small. So we can always assume that they're smaller. So if the -1 index, mid is the element I am on, let's say I'm on this element. If the -1 element exists, if it exists and if it is smaller, if it doesn't exist because it is an or, if it doesn't exist, then we already assume that it is smaller. So we just leave it. So this condition just check that the left element exists and if it is smaller. If it doesn't exist, it is already smaller. How we can doesn't exist? If I have on the very first element, if we are assuming that the very first element is the peak element, then it is also fine because let's say that the array has only one element, it has only 7. That is also fine because if it is only 7, the -1 element and the nth element are already minus negative, which is already like very small. So this should be a peak element. I hope you understand the logic here. So if the left element exists, it has to be smaller. If the right element exists, it has to be larger, like smaller as well. If both of them are smaller, then the element I am on is the right element. It has to be a peak element. Return that. We just got the peak. If not, we have to find out that whether I am on the left side of the mountain or the right hand side. How we can check out? If the like mid plus 1, which is the right element, if it exists and if it is larger, if it exists and if it's larger, which means that I have to somehow go to the right hand side. And if I go to the right hand side, the range should be such that my L should be becomes mid plus 1. And if you have to go to right, like left hand side, R should be like mid -1, but I should not make it mid -1. Why? Because I have to somehow converge to a point. And the converging, if I make the point can be missed if I make mid plus 1 and mid -1. Like this is a very standard thing that we have to only make one L equal to mid plus 1 and right should be mid only. It converges to a particular point. In the end, what if we just somehow got the point, it will return here. If not, the answer will be L. It's a very standard. I have a complete series on binary search. You can watch out that particular thing. I have used this particular logic again and again there, that how you can do binary search to find out things. But I will also put that in this particular, I will put this problem in that particular, you can say playlist as well. So go check it out. I will also put that in the description. So I have a complete, very big playlist of binary search. You can learn it from very scratch. And that's how you can find out the particular peak element of a particular array. That's the complete logic in the code part for this particular video. I hope you understand the logic. If you still have any doubts, you can mention it in the comment box of this particular video. I will see you in the next one. Till keep coding and bye.